Thank you for watching this video. My name is Omri Ben-Eliezer from Harvard University, and this is the long video for the paper Limits of Ordered Graphs and Their Applications that appears in ITCS 2021. This is joint work with Eldar Fischer from the Technion, Amit Levi from the University of Waterloo, and Yuichi Yoshida from NII Japan. In this talk, I will discuss limits of graph sequences. Typically, one thinks about a sequence of graphs that grow larger and larger in terms of number of vertices, and we wish to understand the underlying structure in a unified way. The limit object addresses this need. For dense graphs, where the average degree is of the same order as the number of vertices, the limit is called the graphon, and its theory was established in a series of papers by Borgs, Chase, Lovas, Segedi, Schoch, and Westergombi. Graph limits exhibit an analytical perspective on graph theory that has shown many benefits for various applications. For example, within TCS, many property testing results are much cleaner and seem more natural when stated and proved in analytical language. We will see one such example in this talk. In probability or statistics, graphons give rise to a non-parametric model for distributions over graphs, which is also useful in machine learning applications. In extremal graph theory, again, the analytic perspective usually makes things simpler and easier to prove, and here we will actually see an example. Obviously, in application areas where one is interested in understanding the properties of large graphs or networks, like statistical physics and the theory of networks, graphons are also very relevant as non-parametric models to explain various phenomena. Since the theory of dense graph limits was established about 15 years ago, there has been lots of research on limits for other combinatorial objects. A very popular line of work, where here I only added references to a few representative central works, is on limits for sparse graphs, where unlike the notion of graphons, there is no one limit object that is always correct, and the limit object has to be more problem specific. A partial list of other combinatorial objects for which a limit object was already established includes hypergraphs, permutations, high-dimensional Boolean functions, partially ordered sets, and Latin squares, which are two-dimensional generalizations of permutations. In this talk, I will establish the first known limit object for dense ordered graphs. I will shortly explain what I mean by an ordered graph. Meanwhile, I would like to mention that the above-mentioned work on Latin squares independently developed a limit object for another type of two-dimensional ordered structure, though its scope and applications are different. A graph is ordered if its vertices have a natural ordering. Although one can also consider other structural relations on the vertices. For example, an image can be seen as an ordered bipartite graph, where one part corresponds to the rows, the other part corresponds to the columns, and the edge color between row I and column number j corresponds to the pixel color in location I and j. Clearly, the order of the rows and columns is important for images. Other relevant examples are temporal graphs, where vertices represents events along some timeline and edges represent the interactions between them. This is very relevant, for example, in situations that involve sequential decision-making. Basically, this discussion is relevant for any situation where the vertices are not necessarily symmetric, meaning that they have some underlying structure that must be preserved. Before discussing our limit theory for ordered graphs, let us revisit the classical theory of unordered graph limits and describe its limit object, the graphon. First, to formally define convergence, we need to define some space over functions and describe how to represent finite graphs in this space. For unordered graphs, we go through the following process. We take the n times n adjacency matrix of the graph, where the row and column order does not matter, as we consider unordered graphs. And then we consider a black and white board where each one value in the matrix corresponds to a 1 or a black pixel in the board, and each 0 value in the matrix corresponds to a white pixel in the board. Now that we can describe graphs as graphons, what would be a convergent sequence of graphs? Naturally, we would want graphs with some common behavior to converge to a graphon that characterizes this behavior. A natural candidate for describing the behavior of a graph is in terms of the subgraph densities. In other words, a sequence of graphs converges if for every fixed subgraph f, the density of f in the graphs in the sequence converges. Here, the density of f in G is the probability that a random subgraph of G with the same size of f is equal to f. The limit graphon will have the same subgraph frequencies, where here density is defined by sampling a random subset of points, and for each pair of points we add an edge between them with probability proportional to the value of the graphon on this pair of vertices. As an example, consider the sequence of hereditary random graphs G n 1/2, where the density of any unordered subgraph on k vertices converges to 2 to the minus k times the size of the isomorphism class of the subgraph. Therefore, the sequence converges to the all 1/2 graphon, this one. It's easy to check by definition that the densities match. Convergence of subgraph densities is a notion that is hard to work with, and it turns out that a much more natural notion of the cut distance divided by Fries and Cannon is equivalent and much easier to work with. Here, the cut distance between a pair of graphons is, roughly speaking, the maximum possible integral of the graphon over a rectangle, which is the Cartesian product of two Lebesgue measurable subsets of reals. For example, in a random graph, the integral over any rectangle with non-zero measure should typically equal 1/2 the size of the rectangle, which is the same behavior as the all 1/2 graphon. Now, what is needed to establish a limit theory for certain objects, say for graphs? First, we need a notion of representation for finite objects, finite graphs in our case. Second, we need a usable notion of distance between objects. That would be the cut distance. We already have these two components. In order for the analytical perspective to make sense, that is, that the notion of convergence will be consistent and interesting, we need that the space of limit objects paired with the distance function will be a complete space. By this I mean that any Cauchy sequence, any sequence of objects whose pairwise distances converges to 0, should converge to a limit. It would even be better if the space would be compact, as compactness usually yields regularity lemmas and other useful applications. We also want the limit object to be as simple as possible without unnecessary overrepresentation. Finally, for probabilistic purposes, it will be good to have a limit object that we can sample from. This induces a natural probability distribution. So, can we use a graphon paired with the cut distance as the limit object for ordered graphs? Again, like in the case of unordered graphs, here we assume closeness under measure-preserving transformations. This means the two graphons, W and W prime, where W prime can be generated from W by relabeling the points in a measure-preserving way, should be the same. This is the analytic analog of saying that the order of rows and columns in an adjacency matrix do not matter. The answer is negative. Consider the following simple example. One ordered graph has a clique on the first n over 2 vertices, where I mean first in terms of order, and there are no other edges except for this, the edges of the clique. The other ordered graph is the same, except that the clique is on the last n over 2 vertices. Obviously, these graphs are isomorphic as unordered graphs, so the graphon representations are equivalent. However, the ordered subgraph frequencies are not the same. Consider, for example, the following ordered induced subgraph having 3 vertices and having the first 2 vertices in terms of order connected, and that's it. The other pairs of vertices are not connected. On the right side graph, we do not have this subgraph at all, so the density is 0. On the left side, any subgraph generated by taking 2 vertices from the first half and 1 from the second half works, so the density will be 3/8. Okay, we see that allowing measure-preserving transformations, which made sense when considering unordered graphs, doesn't make sense in the ordered setting. What if we now use the same limit object, but without allowing such transformations? This, unfortunately, also doesn't work. There is a sequence of graphs that converge in terms of ordered subgraph densities, but is not Cauchy with respect to the cut norm. This is the same as the cut distance, but we do not allow reordering. So it seems that the cut norm is just not expressive enough for the ordered case. The sequence is of the odd clique graphs, where all odd numbered vertices are connected by an edge. And just for convenience, we can also add loops on odd vertices, although this doesn't really matter. And there are no other edges except for this clique. Let us see a visual demonstration. So here are the odd clique graphs on 4, 6, 8, and 10 vertices. One can calculate and see that the cut distance between hn and h2n converges to 1/2. So the sequence diverges in cut distance, in cut norm, even though it clearly converges in subgraph frequencies. So cut norm is not expressive enough here. Okay, we want a distance function where large enough odd clique graphs are close to each other. So they form a Cauchy sequence because they have similar ordered subgraph densities. We want them to be a Cauchy sequence because we want them to converge. Trying to understand what makes these graphs similar to each other, note that if we are able to reorder the vertices very locally without changing the order of the vertices too much, we can turn the graphon representing Hn to the graphon representing Hm quite easily. So our findings until now are as follows. First, allowing arbitrary measure-preserving bijections is not suitable for the ordered setting. Second, no reordering at all results in the odd clique examples being far from each other in the distance in the cut norm that we used. And third, slight reordering of the vertices combines the best of both worlds. Odd clique examples are close in when we are able to do some little bit of reordering. But the counterexample for arbitrary measure-preserving bijections breaks down. So let us define the cut-shift distance. In the distance computation, we do allow measure-preserving transformations, but the amount of reordering the transformation applies goes into the cost of the distance function. Would that be good enough? Yes, it turns out that the cut-shift distance characterizes convergence for ordered graphs, in the same way that cut distance works for unordered graphs. Now, are graphons paired with cut shift distance good enough to represent ordered graphs? Unfortunately, the answer is negative. If we revisit the clique sequence, we will need the sequence to converge into a graphon that contains the same amount of odd-like and even-like points in each interval. But this is not possible by Lebesgue's density theorem, a classical result in measure theory, which asserts that no measurable subset of the reals has density 1/2 in every interval. So we need a limit object that is more expressive than a graphon. As we said, for the odd clique example, we would like a limit object that can contain the right proportion of odd vertices and the right proportion of even vertices at any given point. So instead of considering the two-dimensional graphon, which allows us either lots of variability but no sense of order, or a sense of order without enough flexibility, we want a limit object that provides us both order and variability. We call this limit object an orderon. This is a function for pairs of points in R squared, to the interval between 0 and 1. Each pair contains one coordinate that provides a sense of order and another coordinate that provides variability. Recall that we need to say how finite objects, in our case finite ordered graphs, are represented as an orderon. Here we will actually not use the variability coordinate, which will go into play only in the limit object. The representing orderon is a step function where each vertex of the graph is represented by an interval of length 1/n in the order coordinate. Here is a simple visual demonstration of an orderon. For each pair of order and variability tuples, the orderon assigns a value. The cut shift distance now allows measure preserving transformations that have some cost in the order coordinate, but may be arbitrary in the variability coordinate. Now, our first attempt would be to use orderons as the limit object, coupled with the cut shift distance. And as you might expect, this attempt actually finally succeeds. The limit object for the odd clique sequence will be one where for any value of x, the order coordinate, half the variability interval consists of odd particles that belong to the clique, and the other half consists of even particles. The value of the orderon between a couple of odd particles is 1. This corresponds to an edge, and it is 0, a non-edge, anywhere else. Now, let us state the main results of our theory. The first result is the completeness theorem, which states that in the space of orderons, any Cauchy sequence in cut shift distance is an orderon limit. In particular, this means that any sequence of ordered graphs with the convergence ordered subgraph densities has a limit in the orderon space, which demonstrates the same subgraph frequencies. The second result asserts that the space is not only complete, but also compact. Every sequence of orderons has a convergence subsequence. An equivalent formulation is that any collection of open balls in the space has a finite subset which covers the space. This is useful for obtaining regularity lemma type results, and we will actually see one such result soon. The next result is a sampling theorem, which considers the following sampling procedure. Take k points of the form xi and ai in the orderon, and consider a random ordered graph on k vertices, where the probability for an edge between vertices number I and j is the value of the orderon between xi and ai, and the other point xj and aj. then with high probability, the sampled graph is close in Kashif distance to the original orderon. An immediate corollary of the sampling theorem is the density theorem, which states that for any orderon, there is a finite ordered graph that is arbitrarily close in Kashif distance to it. Specifically, if you want distance epsilon, then there exists such a graph of size exponential in 1 over epsilon. The last, and perhaps most interesting main result that I would like to mention is the pixelization lemma. Let us define a pixelized orderon as a finite description orderon that has k types of order blocks and L types of variability strips, and the value of the edge between a pair of tuples corresponds only to the block and strip pair that each of them belongs to. This is actually a slightly simplified picture of the actual definition, so feel free to see the paper for more details. The pixelization theorem now states that any orderon is arbitrarily close in L1 distance to a pixelized orderon, with the added property that any subgraph that does not appear with positive density in the original orderon will also have zero density in the pixelized one. Conceptually, this is basically a strong analytic ordered regularity lemma for orderons. It means that any orderon can be approximated with small L1 error by a finite description orderon without any additional noise. So without any artifacts that appear in the original orderon. Let me remark here that being close in L1 distance trivially means also being close in cut distance. So this statement does not follow from any of the previous results. And in fact, this result requires some additional tools to prove it. Now, let me conclude with a couple of applications of our theory. The first application is a new proof of the ordered graph removal lemma that we recently proved with Eldar and Fischer. The removal lemma considers hereditary properties of ordered graphs, whereby hereditary I mean a property that is closed under deletion of vertices, for example, being bipartite or not containing an induced copy of a cycle on 4 vertices, C4. And the removal lemma states that any hereditary ordered graph property is testable with a constant number of queries. This is a substantial generalization of well-known graph removal lemmas that do not take order into account. The original proof of the ordered graph removal lemma is complicated. It's more combinatorial in nature, and it mixes several regularity type ideas with flow-based rounding techniques and a new type of Ramsey lemma that is robust to noise. The new proof that we were able to get using Orderon, using ordered graph limits, look much simpler than the combinatorial proof. And this new proof uses compactness, pixelization, and in addition, just a standard Ramsey lemma. It's also much shorter. As I mentioned in the beginning of the talk, there are many situations where the analytic perspective is more natural and leads to simpler proofs. This is one such example of this phenomenon. The other application concerns an interesting line of work in experimental combinatorics. Given any hereditary property of unordered graphs and another graph, one can ask what is the Hamming distance between the graph and the hereditary property. This is the minimal number of edges that we need to add or delete in the graph to satisfy the property. A beautiful and surprising result by Alon and Stav shows that for unordered graphs, for any hereditary property that there exists a probability P, so there exists some probability P, depends on the property, so that the Erdős-Renyi random graph model GNP generates with high probability graphs that are asymptotically the furthest away from the property. For example, For the property of not containing an induced copy of C4, the cycle of on 4 vertices, it is easy to see that any graph is of Hamming distance at most 1/2 to the property. But it also turns out that Gn 1/2 is typically almost 1/2 far from the property. And one may naturally ask the same question in ordered graphs. The bad news are that this theorem is no longer true for ordered graphs. There is an example of such an ordered property where GNP is at most 1/4 far, while the furthest ordered graph from the property is actually almost 1/2 far. However, the good news are that we do prove a weaker but more general version of the unordered result that works for ordered graphs. This is the first result of this type. What we show is that for any hereditary property of ordered graphs, there exists an ordered stochastic block model which generates ordered graphs that are asymptotically the furthest away from the property. Here, a stochastic block model is a very well-known generalization of the hereditary model, where there are a constant number of types of vertices, and each vertex is randomly assigned a type. Then, each pair of vertices is randomly connected by an edge with probability that only depends on the pair of types considered. By ordered, I mean the types corresponds to intervals in the ordering of the vertices. That's it for today. Let me state several interesting questions left for future research. First, we focused on more combinatorial applications of the ordered graph limit theory, and we did not look into probabilistic or statistical models that Orderons naturally induce. I mean, we did prove the sampling theorem as one of our main theorems, but we didn't explore it any further. This should be interesting for generative models in applications like temporal or causal graphs, where there is an underlying order on the vertices that graphons or other limit objects cannot directly capture. Another interesting line of research is to develop limit objects for ordered structures that are the limit objects are less global in nature. Our limit object is suitable for dense ordered graphs. It's more global in nature, and it would be interesting to look into models that are sparse or more local in terms of the ordering. The sparse line of research is very active for unordered graphs, as we mentioned before. Okay, thank you for your attention. Feel free to drop an email if you have any questions or to talk at the conference. See you.